This is our first notes of our new unit on series. This unit is going to deal with convergence and divergence of series. And on this first day, we're going to get two tests which will determine convergence and divergence of certain series. Before we get going on that though, we need to do a little factorial refresher and just a little refresher on the basics of sequences and series. For the factorial refresher, remember that this notation, 5 with this exclamation mark after it, that's our notation for factorial. And it means, this would mean 5 times 4 times 3 times 2 times 1. And we will get to where we recognize the values of these. 5 factorial is 120, and you'll get to where you recognize that immediately. 1 factorial is 1. If you multiply that by 2, you get 2 factorial, which is 2. If you multiply that by 3, you get 3 factorial, which would be 6, because 3 times 2 is 6. If you multiply 6 times 4, you would get 4 factorial. And if you multiplied that 24 times 5, you would get 5 factorial. If you multiply that by 6, you'd get 6 factorial, etc. 0 factorial is 1. And there's a pretty quick proof for that I will show you here. N factorial would be n times n minus 1 times n minus 2 times n minus 3 all the way down till 1. Yeah? That means that n factorial is n times n minus 1 factorial, because this whole thing is n minus 1 factorial. So if we let n equal 1, then we get 1 factorial is 1 times 1 minus 1 factorial, which means 1 factorial is 1 times 0 factorial, which means those two things have to be equal. Therefore, 0 factorial must be 1. 0 factorial is 1. So we will remember that. 0 factorial is not 0, it is 1. N factorial is, as we said above, n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So this expression will be n times n minus 1 times n minus 2 times n minus 3 all the way down to 1 divided by n plus 2 times 1 less than that, which would be n plus 1, times 1 less than that, which would be n, times 1 less than that, which would be n minus 1, n minus 2, all the way down to 1. So we find that when this happens, things cancel out. This n minus 2 would cancel out with the next term up here, the n minus 2 there. I'm sorry. This n minus 2 cancels with this n minus 2. There would be an n minus 3 next, which would cancel with that n minus 3. All of these things would cancel with all of these things. N minus 1 cancels with that n minus 1. N cancels with that n. We're left with 1 in the numerator and n plus 2 times n plus 1 in the denominator. We will need to be able to reduce factorials like that when we're doing one of our tests for convergence. Okay, so when I see this, I think to myself, which is bigger? N plus 2 is bigger than n. So the n factorial will all cancel out, and all I need to do is find out what's left after I expand n plus 2 factorial. And that would be the n plus 2 times n plus 1, because the next term would be n, which is where we're at on top. Okay? All right. A sequence is just a list of numbers in a pattern. We call a sub n the nth term of the sequence. Okay? That's a review from last year. This is all a review from last year so far. A series is the sum of the terms of a sequence. So if you take each of these and add them all up, you get a series instead of a sequence. A sequence is just a list. A series is a sum. We abbreviate a series using sigma notation. This is our counter. It tells us what we're starting at. In this case, we're starting at 1. And a series is going to infinity. An infinite series is going to infinity. We can also have a partial series, which is not going to infinity. It would be stopping at a finite number. Okay? For this unit, when we say series, it is meant to be an infinite series. If it's a finite series, we will say a partial sum or a partial series. We can start the n at any number. So we will need to be careful what we're starting n at, what we're given that to be. If you see a series without that n equals something to infinity, it is assumed to go to infinity. The bottom number is not assumed, it is taken to be the previously defined number. So if you are given a series that says this, you can, in your problem, you can write that as just this, and it is assumed to be the same information that was originally given to you. The nth partial sum is the sum of the first n terms. So the third partial sum is the sum of the first 3 terms. The fifth partial sum is the sum of the first 5 terms, etc. And this is denoted S sub n. This is the sum of the first n terms. The entire infinite sum is denoted by a capital S with no subscript. That means that this sum is S. We say that an infinite series converges if the limit of its sequence of partial sums exists and equals S. That means that S sub infinity, if you added up the first infinite terms, you would get a finite real number. Okay? That would be the limit existing. I shouldn't write it like that. If the limit as n goes to infinity of S sub n is equal to a real number, we say that series, the infinite series, converges. If it does not, then we say that the series diverges. A series can diverge if this limit would be infinity, negative infinity, or if that limit oscillates between numbers, etc. If it does not come to a single real number. Okay, so that's what I just wrote up here. In this unit, we're going to be concerned with 2 questions. Number 1, does the series converge or diverge? And number 2, if the series converges, can we find its sum? And if so, what is its sum? We're going to find that there is only one type of series in this unit for which we can find an infinite sum. We're going to learn 8 tests for determining whether a series converges or diverges. Okay? In most cases, in all but one case, we will not be able to find the actual sum. Okay? Alrighty, our first test is called the nth term test for divergence. That is the official name, the nth term test for divergence. Well, this tells you that this test can only be used to state that a series is diverging. It cannot be proved, it cannot be used to prove convergence, only divergence. And it's really simple. If you have a series, a sub 1 plus a sub 2 plus a sub 3 plus on and on, plus a sub n plus I on and on. If you have a series and these terms are not going to 0 eventually, as the series goes on, if these terms are not going to 0, then this series has got to diverge. If these are not going to 0, then this series is going to either infinity or negative infinity. That's that. So these terms have got to go to 0 if a series has any hope of converging. So if the limit as n goes to infinity of a sub n is not 0, then the series diverges. If it does go to 0, then the series might still diverge. We just don't know. So notice that this does not say if the limit is 0, then the series converges. If that was the case, then we would not have 8 tests for convergence and divergence. We would have 1 test, and it would only be the nth term test. So if these terms do go to 0, it tells us nothing. Maybe the series converges, maybe it diverges, we don't know. We have to go use a different test. Okay, and there are only 8 tests. I need to correct that. Alrighty. Okay, examples. Let's determine whether the following series converge or diverge. So this is the way our instructions will read in this unit, and so I kept it that same way, but we only have 1 test right now. We only will be able to show that a series diverges. So we'll need to keep that in mind. All right, so when we have a series, and we'll be given a series, does it converge or diverge? The first thing you always want to do is check out the expression here. This is your a sub n expression. And we want to know, does the limit as n goes to infinity of a sub n, does that go to 0? So we're using our little limit here. What is this limit? Well, as n goes to infinity, the plus 3 and the minus 5 have no significance as n is going to infinity. The only thing of any significance is 2n over 3n. The n's reduce, and this leaves 2/3. 2/3 is not 0. Therefore, the series diverges by the nth term test for divergence. Okay? Let's go on to the next one. Does this series converge or diverge? So I see my a sub n, and first thing I do is I check out what would happen if I let n go to infinity. And if I let n go to infinity of this expression, the plus 1 does not matter. So I'm left with the limit as n goes to infinity, of n factorial over 2 times n factorial. Notice that that is not 2n all factorial. It is 2 times n factorial. Okay, so this reduces. The n factorial is reduced to 1 over 2, which is not 0. Therefore, the series diverges by the nth term test for divergence. Okay, next up, limit as n goes to infinity of 3 to the n minus 2 over 3 to the n. Well, the minus 2 does not matter when we have 3 to the n on top with it. So the minus 2 is insignificant. I can ignore it. It's like it's not there. The 3 to the n's cancel, and it leaves 1, which is not 0. Therefore, the series diverges by the nth term test for divergence. Next up, this one. Well, limit as n goes to infinity of 1 plus 1 over n to the n. What is that limit? And we know from our study of L'Hopital's rule that this limit, this is one that we have to recognize. I need you to recognize this limit. When you see this limit, I need you to recognize that that is e. And it's e to the first because there's a 1 right there. This number right here tells you what the exponent on the e is. So that is e. It's the definition of e. It is the formal definition of e. So this limit is e, which is not 0. Therefore, the series diverges by the nth term test for divergence. Okay. Well, when I see this one, I recognize it already. The limit as n goes to infinity of this a sub n is e to the fifth, which is not 0. Therefore, this series diverges by the nth term test for divergence. Okay. Next up, limit as n goes to infinity of 3n factorial plus 2 over 9 to the n plus 7. What is the highest powered term on top? What is the highest powered term on the bottom? I see Big Mama on top. 9 to the n is very strong, but not nearly as strong as n factorial, Big Mama. So Big Mama's on top. This thing goes to infinity, which is not 0. Therefore, this series diverges by the nth term test for divergence. Okay, next up, limit n goes to infinity, 2 to the n minus 17 over n squared plus 4n plus 10. Highest powered term on top, highest powered term on the bottom. We can ignore everything else since n is going to infinity. And 2 to the n is stronger than n squared, so this whole thing goes to infinity again, which is not 0. Therefore, the series diverges by the nth term test for divergence. Last up, write this down. Okay, highest powered term on top is this n cubed. We could ignore everything else since n is going to infinity. There's only one term on the bottom, and it's a natural log. Natural log is going to infinity, but not fast. Not nearly as fast as n cubed goes to infinity. So this whole thing is infinity, which is not 0. Therefore, the series diverges by the nth term test for divergence. Okay, so nth term test, what you want to look at to use the nth term test. For the nth term test, in your expression, you want to glance at it and ask yourself, is there more power on top than on the bottom? Is it top heavy? Top heavy means you can use the nth term test for divergence because that limit will not be 0. Okay? Is it top heavy? Look at your a sub n. Is it top heavy? Sometimes you're not going to be able to tell immediately. Like, this is not top heavy. It's not. In fact, the top with that minus 2, it's less than the bottom. However, the nth term test still works. But in many cases, you can quickly look at it and ask yourself, is this top heavy? And if it is, we can use the nth term test for divergence. Okay, next up. The next test, our second test that we're going to look at, is our geometric series test. So let's remind ourselves, geometric series, this is something that you guys did in pre-cal. So this thing will be a review. This little section will be a review. Okay, if we expand this out, we start with n as 1. So if I put a 1 in there, my first term is 1/2. Plus, my second term is 1 squared over 2 squared. So 1 over 4. Plus, next term will be 1 cubed over 2 cubed. The next term will be 1 cubed over 2 to the 4th. Then 1 cubed over 2 to the 5th. 1 cubed over 2 to the 6th. And this would go on and on and on. Okay? This is a geometric series because each term, each consecutive term is multiplied by a common ratio. To get from one term to the next term, we multiply by the same thing every time, and we are multiplying by 1/2. Okay, a geometric series can be written in this form: a number times r to the n, where r is that common ratio. You can always find a common ratio by taking any term and dividing by the term in front of it. Okay? All right, the starting value of n is irrelevant when determining whether the series converges or diverges. Okay? And a geometric series, if you cannot use the nth term test, this series converges if it's geometric, and that will happen if the absolute value of r is less than 1. So here is the geometric series test. A geometric series with common ratio r diverges when r is greater than or equal to 1, and converges when the absolute value of r is less than 1. Furthermore, if our geometric series converges, if we have a convergent geometric series, then we can actually find its sum. This is the only type of series, this unit, where we can find the sum. Next unit we'll have more. But for this unit, this is the only one that we can actually find the sum, and it's the first term of the series over 1 minus r, and I need you to know that. I need you to know all these tests, and I need you to know that formula for finding the sum of a convergent geometric series. Let's take a look at some examples. In this first example, this is already in the form of a geometric series. Remember, the form of the geometric series looks like that. A number, which in this case would be 1, times r to the n. So this is geometric. It is geometric. R is equal to 3/2, and that means the absolute value of r is greater than 1. Therefore, the series diverges by geometric series test. Number 2. Well, this isn't quite in the form of a geometric series yet, okay, but we can pretty quickly get it in that form. I'm going to rewrite this as, and notice I'm not going to put the n equals 1 to infinity, okay, because I already know what n is equal to 1. I already know that here, so I'm not going to rewrite it here. The 3 I'm going to leave on top, and whenever I have a number being raised to an n power on the bottom, I can write that as 1 over that number all to the n because 1 to the n is 1. So I can write it like that because now I see what r is. This is geometric. R is equal to -1/2. The absolute value of r is less than 1, therefore the series converges by geometric series test. And since it converges, we can find its sum. So I'm going to find its sum. The sum, capital S, is the very first term over 1 minus r. Well, I know on the bottom I'm going to have 1 minus a -1/2. What is the very first term? The very first term occurs when n is this number, and that's 1. So this will be 3 divided by -2 to the first power. That is -3/2. So the very first term is -3/2. So this would be a safe stop spot for finding the sum. However, these will be multiple choice questions, so let's simplify this. We've got, and to simplify this, I'm going to multiply, let me get an orange here, multiply by 2/2 because of this little denominator here. This is a quick way to simplify a complex fraction. On top we have -3. On the bottom we have 2 times 1 plus 1. That is -3/3, which is -1. So the sum is -1 there. All right, for this one, next one, I can rewrite this as pi over e all to the n power. And then it's in the form of a geometric series. So this is geometric. R is equal to pi over e. And the absolute value of r is, okay, is this greater than 1 or less than 1? Well, pi is 3 point something. E is 2 point something. So the absolute value of r is greater than 1. Therefore, the series diverges by geometric series test. Okay, if it diverges, it's going to go to infinity or negative infinity. We could quickly find out, but we're not asked to do so. All right, number 4. This looks a little bit complicated. I'm going to blow this up so you can see this a little bit better. Oops, blow it up a little bit. Okay. All righty. There we go. All right, so is this geometric? Well, it doesn't. It's hard to tell for right now. So let's simplify this thing. Not simplify it. Let's change it. Let's modify it. I'm going to use the property of exponents that says this is e to the n times e squared. I'm going to write that as e squared times e to the n. And that's true because when we have the same bases, we add the powers. On the bottom, this is pi to the first times pi to the n. And this is e squared over pi times e over pi to the n power. And now it's in the form of a geometric series. So yes, this is geometric. R is equal to e over pi. The absolute value of r is, we're comparing it to 1, is this bigger than 1 or less than 1? It's not equal to 1. So is it bigger than 1 or less than 1? Well, this is less than 1 because e is less than pi. So therefore, the series converges by geometric series test. Okay, if it converges, we can find the sum. So let's find the sum. Get my other color here. All right, the sum is the very first term over 1 minus r. So on the bottom, I know I have 1 minus r, which is e over pi. What is the very first term? Well, the very first term occurs when n is 0. When n is 0, I think I'm going to go over here, because when n is 0, I have e to the 0, which is 1, over pi to the 0, which is 1. I have e squared over pi. So the very first term is e squared over pi. To simplify this for a multiple choice question, I'm going to multiply top and bottom by pi, and this would be e squared over pi minus e. Multiple choice question answer. Last example. For what values of k does this thing converge? Well, this is geo. This is a geometric series. It's in the form of a geometric series, and R is k over 5. Well, this converges if the absolute value of R is less than 1, right? So we want for the absolute value of k over 5 to be less than 1. What does it take to do that? Well, the absolute value of k is less than 5, because I shouldn't have done it that quickly. This would be the absolute value of k over the absolute value of 5 is less than 1. The absolute value of 5 is just 5, and I'm going to multiply it to the other side and get that. So the absolute value of k is less than 5, which means k is less than 5 but bigger than negative 5. It's between negative 5 and 5. And those are the values of k that make that series converge. So this has been the nth term test for divergence and the geometric series test, which can be used for convergence or divergence. And we also learned how to find the sum of a series, of a geometric series, if it converges.